Well, I have had some considerable difficulty recording this today. Um, my technology has not been working well with me, so hopefully on this now third take, I can get this through. So, in Chapter 7, we started dealing with functions of two variables. Although we will discuss instances where there's more than two variables involved. We're going to focus our attention on situations involving functions that have two different variables as part of its domain. And that's what they kind of go through in these definitions here, is that now my domain is going to be a set of ordered pairs, and the range is going to be, a function value based off of, how the function is defined. So instead of having x being the one variable, y being the range value, now x and y are part of the domain, and the range is going to be f of x, y. More formal definition here. I'm not going to go through some of these parts here for the interest of, hopefully if I keep the video to maybe a little bit shorter, maybe the technology won't revolt against me. I don't know. If the domain is not stated, it's always taken to be that the largest set of ordered pairs for which the function is defined. So sometimes if they don't tell you what the domain is, you have to kind of be able to interpret what the domain is, which is why they're going to ask you some questions early on about knowing what the domain of the function is. So, for example, if you're given this function f of x, y being the square root of x over y squared, they want you to find first the domain and then what f of 9 negative 1 is. Well, I can see that x is underneath a square root symbol, so x has to be greater than or equal to 0, and of course y can't be 0 because it's going to create a 0 in the denominator. We're often going to use set notation for this. The reason being is interval notation helped us define things in a way that we could kind of see how that would look on a number line. And a number line can be used pretty well to describe a domain when I only have a single variable involved. For two variables involved, then my domain is actually sets of ordered pairs, or I'd basically look at an area on a coordinate system. So having interval notation does not necessarily help me that much, although I could probably make up interval notation for these two parts here. Since I'm already using set notation, there's really no point to it. So that's why you're going to see set notation and some standard operators like this rather than see the interval notation at this point. Don't forget about interval notation though, because interval notation is used a lot in more advanced calculuses, especially if you're only dealing with one variable. So it's not, don't let that just go by the wayside. As far as b goes, f of 9 negative 1. The first thing is, take a quick look to see this. I mean, it's in the domain. I mean, 9 negative 1's in the domain because the x value is greater than or equal to 0. Negative 1 is not 0, so it fits that rule very well. And all I'm going to do is what I did before. I'm just going to plug the values in where they belong. So I'm going to get the square root of 9 over negative 1 squared, which when I simplify it becomes 3 over 1 or 3. Some functions that we deal with two variables, we've seen the area being length times width before. And in some of the cases we looked at earlier, we would usually have some way of putting length in terms of width or width in terms of length to make it one variable. And you're still going to have instances being given to you that you could probably still put it in terms of one variable. It just, it's not going to, they're going to ask that you try to do it using this other methods that we're going to be looking at, so that, you can always go back to the older method to kind of check to make sure you get the same result. Of course, other situations like the next function they give us down here, the length of a skid mark, since, the weight of the vehicle and the velocity of the vehicle is not going to be necessarily the most direct relationship between the two. Whereas with area being length times width, if I only had a certain amount of material to use, then whatever wasn't used for the length was used for the width. So they kind of depended on each other as well. Whereas, the weight of a vehicle and its velocity do not necessarily relate to one another. So you won't necessarily have a means of putting one in terms of the other in that kind of respect. So some of these things we're going to learn about, are necessary when I especially dealing with circumstances where I can't do that for one reason or another. So, getting into a chance for you to try some things out. Here is a function f of xy equaling the natural log of x cubed minus y squared. I want you to tell me what its domain is, and I want you to tell me what f of e comma 0 is. Well, as far as the function f of xy, what its domain is, well, I know this value here has to be greater than 0. Because if it isn't, I wouldn't be able to take the natural log of it. And just solving the inequality a little bit, I would have to get that x cubed is greater than y squared. To tell you with all honesty, that's just the way I'm going to keep it when I state my domain. It's a set of all points such that x, y. Because if I start trying to cube root both sides or square root both sides, I can start losing some variables. Although the cube root, not necessarily so much. So sometimes, instead of having x and y listed as two separate things, you may have to express the relationship as, how the two need to relate to each other in order for it to work. Because I can't just say, well, x could be this and x can't be that. Well, x could be some values and, and not be those values. It depends on what y is. So there'll be some instances where I say, well, x could be 1 as long as y is, a number less than 1. But x can't be 1 if y is, say, 2. So there's certain ordered pairs that just don't work. Whereas, I can't say well, y can never be 2. Well, it can if x is this amount or that amount. So it's really dependent. I can't just make the list separate because there is some interdependence upon them in this kind of circumstance. So as far as f of e0. Again, all I'm going to be doing is putting the right things in the right spot. So I'm going to have e to the third power, because that takes the place of the x, minus 0 squared. And I can already see, if I cube e, it is more than 0 squared. So, this is in my domain. Natural log of e cubed. And of course, when I do the natural log of e raised to a power, these just kind of cancel out, leaving me with 3. They also show you some work with the fact that you could have more than 2 variables involved. And here's some functions that would do that. And although the textbook has some problems in there, and I may give you 1 or 2 here and there where you have more than 3 variables involved. I'm not necessarily, when we start doing some of the work with them, like optimizing it and things like that. You can see that on the list of problems you're expected to do from each chapter, that most of those problems are skipped, because we just want to stick to the 2 variables, because it gets more and more complicated even using the methods that we're going to be using to do more than just 2 variables. So, but these are some examples of some functions that you could create using multiple variables, more than 2. And for instance, if you wanted to do a problem like this, where you're asked to find, the domain and things like that, it works the same way. Just you have more of a list. So here, when I look for the domain, x has to be greater than or equal to 0 for it to work with the square root. Y can't be 0. Z has to be more than 0, because it can't be 0 because 1 over z won't exist at that point, and I can't take the natural log of something that doesn't exist. And if z is less than 0, then I start getting a negative value, and I can't take the natural log of a negative value. So I would just list those 3 things as my domain. As far as the range goes, again, I'm just going to plug the numbers in to x, y, and z. Always a good idea to take a look and make sure it fits the domain values. Kind of coming back to this, I can see 4 is greater than or equal to 0. -1 does not equal 0. 1 in the third position is more than 0. So it fits my domain. So when I plug it in, I know I'm going to get some sort of answer. Simplifying, I can see the natural log of 1 becomes 0. So I'm left with 2 over -1, which is just -2. So your turn for this function here, which is in 3 variables. What is its domain, and what is f of 4 e to the -1? Or what's f of 4 comma e comma -1? Sorry. As far as the domain goes, again, when I look at the letters x, y, and z, I can see, x has to be greater than or equal to 0 because, it's underneath the radical and those are the numbers that'll work. Y has to be greater than 0 or it won't work with the natural log. Z really has no restriction. So Z could be anything. So I could write the domain as x greater than or equal to 0, y greater than 0. Oh, I don't know why I keep wanting to put that down there. All 3 takes, I put that down there. Ugh. Try to avoid it, but... And it's optional. I don't necessarily have to write this part. Well, before I put that part in. I could say z is a real number. But I really don't have to state that part because that's basically saying it's not restricted for the z's. These are just saying, okay, these are restricted. And I'm assuming all real numbers besides those. So it's really up to you if you want to put that last part in. Since it's not a restriction, it's basically saying, okay, z is unrestricted, and you really don't have to list it at all. Now, as far as f of 4e -1, again, I can see really easily that that order triple is in the domain. 4 is greater than or equal to 0. E is greater than 0. -1's a real number. So I'm going to do -1 because that's what z was times the square root of 4 times the natural log of e, which gives me -1 times 2 times 1, which is just -2 again. So nothing very difficult about it. As far as graphs go, they mentioned some graphing things. We're not going to ask you to do a whole lot of graphing things. It's kind of hard to draw a 3-dimensional graph on a 2-dimensional surface and be very accurate about it, which is why you should be happier in business calc compared to standard calc, because sometimes they do want you to create some of the graphs to a certain extent, and it gets to be kind of complicated to make it look, in a way that's clear. But it kind of shows you the difficulties of dealing with graphs when you have multiple variables involved, because, well, first of all, you can only deal with two variables as a domain and a third variable being the range. So here, we would let z be, f of x, y. And of course, the xy plane is considered to be on the flat surface here. The reason being is if I started having more variables, I had to make a 4-dimensional graph. Well, we don't live in a 4-dimensional world, so I can't even create anything that would be able to be a good model of a 4th-dimensional graph. I mean, so. But it shows you some of the, how you would plot points. Something you don't have to worry necessarily about. They showed an example here of how this is graphed when we set z equal to f of xy. And the whole reason behind this is that, as I plot all the points that would fit on this, I can see that we get a graph. This is more of a 3-dimensional graph. And as you can see, we can actually reach critical points. We can actually reach, a maximum in this case. When we start dealing with 3-dimensional graphs, though, especially when I have multiple variables involved, I could have critical points, and I could have what we call saddle points, which we're going to get into. Saddle points will often show up as part of the same test that we're going to use to do optimization, and we will get to optimization as we move along with this. So, but just to kind of go into some more detail, and I'm not going to go into this in great depth because the graphing portion of it is not as important to us. The reason being is, again, you're trying to make a three-dimensional graph, okay? But the one skill we want you to be able to do is to be able to, you know, if multiple variables are involved, whether it's two or more needed, to be able to write expressions that represent them. So, for instance, here, as you can see, if we were taking one big piece of cardboard and cutting these things out, there could be some ways of relating these all to each other because of the fact that, you know, if I have a set amount of cardboard, then, you know, the dimensions z, y, and x are going to be restricted upon, you know, the size of what I had the material to work with. But for the time being, though, we want to construct this open top box, and as you can see, it has a bottom that has dimensions x, y. It has a height of z, and you can see there's two partitions in the middle that kind of split it into three sections. So what I want you to do for this is to come up with a formula involving x, y, and z that would represent the volume of this box, and then the amount of material needed to build the box. And just to give you a little hint about that, when you're asked for total amount of material to build the box, they're asking for surface area, which means I'm looking for the total area of the surfaces. So, take a pause a moment and see if you come up with some formulas for these. Well, volume is kind of easy because of the fact that, you know, it's length, width, and height. And I can see, you know, here's my width, here's my length, here's my height. So my volume with respect to these three variables, because all they're really doing is taking the place of length, width, and height, is just going to be x times y times z. I can put the multiplication symbols in. I don't necessarily have to. The surface area is a little bit more complicated, because when I do the surface area, if I get my pen to work, in terms of x, y, and z, I got to look at, you know, each surface, each of the surfaces I have. Some of them are repeated, some of them are not. For instance, I have the bottom of the box. Now, it looks like three different bottoms, but it's just one bottom that has partitions in it. And I can see that its dimensions are x times y. So I'm going to say that's going to be x times y. That takes care of the bottom. There's no top, so, you know, I don't have to worry about that. But I still have more parts of the box that I'm building. So another part of the box would be my front and my back. Now each one of those has a dimension of x times z. So I'm going to say I'm going to have, I don't want that. I don't know what that happened there. I'm going to have 2 times x times z, and again that's going to take care of front and back. And lastly, let's pick a good color here. I have these sides. I have this side here, but also these partitions are the same dimensions. This one here and this one here. So I have 4 that have dimensions y and z. So when I write this, 4 times y times z, and that's my left, right, and partitions. Although you're not going to actually be doing much with volume necessarily, you might be asked for some situations with surface area, although 3 variables are involved in that one too. what we start looking at when we do optimization, when we use multiple variables, is that we'll often look to use one function as a constraint for the other. And that's what we were doing before. If we only had a set amount of material to use to build a fence and we're looking for an area, that would be, the area could be maximized with the constraints that, my x's or my length and width could only be so much because of the material I had to build it with. Very similar with volume and surface area as well. If I only have a set amount of material to use, then the volume can only be so much, and I can see if what I can do to maximize it and what the dimensions would be. Or if I knew it had to be a certain volume, I can see, okay, what's the minimum amount of material I could use to make that. Those are the situations we'll deal with. And you might be posed a question with that, but it's going to take it does take some time to do it with 3 variables. Most of the circumstances you're going to be responsible for, and the only ones you're going to be responsible for tests and quizzes and whatnot, are going to be dealing with 2 variables. So that's a good side note there, but you might be asked to do some practice with multiple variables just to get used to equation solving techniques and things like that as well. So I did mention about optimization. So let's talk about optimization a little bit, because there are several different types of things you can see in 3-dimensional graphs. I mean, of course, you have a relative extreme point. So you can have a relative maximum. And the thing you want to keep in mind about the relative maximum, if I make sure I could, is like, when I look at like on the XY plane, or like when I look at, the XZ plane and the YZ plane, in both cases, I'm reaching a maximum point. Whereas when I look at, the minimum here, here's my YZ graph. My XZ graph will look something along the lines of this. In both cases, I'm reaching a minimum. So, if both of those planes are reaching a minimum at the same time, it's a minimum. So, I actually have to have 2 different 2-dimensional graphs reach a minimum at the same time for it to be considered a true relative minimum. They go to some more sophisticated graphing looks here, but there's another thing that's going to show up when 3-dimensional graphs, and that's called a saddle point. And a saddle point results from, as they show you here, I have this function right here. This would probably be more like my YZ graph, where I'm reaching a minimum. That's the look of it. It could do the same thing with the XZ graph, and of course it made it. So I have this one right here where I'm reaching a minimum, but I have this one here where I'm reaching a maximum. That's what we call a saddle point. It's not considered an extreme point because it doesn't reach the same extreme point in both of those planes. So, but when I start doing tests that we're going to look at momentarily as we go more into this unit, especially in section 3, when I start looking for dimensions and looking for maximums and minimums and do optimization, there's certain tests we do. These saddle points will come up in those tests, and we have to be able to differentiate between them. The way that you're going to handle it in some cases, because there's some methods we use to identify that, and there's another method that we're going to use in section 5 where we have to assume that we reach. If we're looking for a minimum, we have to assume that the critical point we find is a minimum, and if we're looking for a maximum, we assume the point we find is a maximum. If I find multiple points and know there's a minimum and a maximum, I'm just going to find the one that reaches a maximum, one that reaches a minimum, based off of the function value. And that's not necessarily the best search pattern because that means that we're only looking at very specific functions at that point. But to get into identifying them ourselves involves a lot more things than this course is actually designed for us to learn about. But we will see these saddle points sometimes come up. We'll talk about them, and sometimes in some cases being able to tell if we have one or not versus a critical point or a relative max or a min. So, but they do show some of these graphs in the book. I'm not going to spend a lot of time with it. They kind of show some of these points here. I'm not going to spend a lot of time with that. In section 2, we start dealing with partial derivatives. And partial derivatives are what we're making use of in order to do the things that we're going to be asked to do in sections 3 and 5. Because remember, when we did optimization, we were finding minimums and maximums using derivatives. Well, we're going to be asked to do the same thing, except the derivatives are going to be partial derivatives. So what do we mean by a partial derivative? Here they just kind of briefly review some of the things, some of the rules we talked about. And they start with the very basic rules for derivatives that we had before. The most important one that we're going to look at, and the reason why they mention this, is that what we do with a constant and a constant multiple. The reason being is when I do partial derivatives, I could take, for f of x, y, I could do 2 partial derivatives. And if I have more variables, I could do even more partial derivatives. And sometimes you're going to see, they call these things curly D's. I believe they are Greek letters. I don't know what Greek letter it is. I know it's a lowercase one, but I'm trying to remember I don't remember what it is on top of my head. But when you see that kind of notation, and we're going to see that notation, but we're going to use another one more primarily, and then you'll see an example of that momentarily. That means I'm doing a partial derivative, and so therefore, when I see the dx down here, that means I'm doing a partial derivative with respect to x. This means I'm doing a partial derivative with respect to y. And as it's saying here, when I do a partial derivative with respect to x, that means that I'm treating essentially x as the variable. The y is being treated as a constant. So that's the top one. Whereas when I do a partial derivative with respect to y, and that's how I read this stuff. I always say it's partial derivative with respect to y. That means I'm going to treat y as the variable and x is being held as the constant. So we're not going to do any limit definition stuff with that, because it gets to be even more complicated. But kind of summary here, which we just kind of mentioned before. So as an example, if you were asked to do the partial derivative with respect to x of x cubed y to the 4th, that means that in this circumstance, the x to the cube part is what we're going to be taking the derivative of. The y to the 4th is going to be treated as a constant multiple. So when I do the derivative of this, the partial derivative of this, the partial derivative of respect to x, the derivative of x cubed is 3x squared. The y to the 4th is a constant that we just kind of carry along. And then I'm just going to, I could pretty it up a little bit if I need to, but this one is pretty much, the way it's set is pretty good. The derivative with respect to x, the partial derivative with respect to x is 3x squared y to the 4th. So now let's have you try the converse of that. Find the partial derivative with respect to y for the same function. Well, for this one here, since we're doing it with respect to y now, this is the constant. It's a constant multiple. So I'm going to kind of keep that along for the ride. The derivative of y to the 4th power with respect to y is going to be 4y cubed. And so if I pretty this up a little bit, I'm going to have 4x cubed y cubed. So it's not very difficult. It's just making sure you're paying attention to what's being treated as a constant, what's being treated as a variable. Now, the notation we're going to see used most often from this, from the next sections is going to be this notation here. And a lot of times, they're not even going to have the xy part. Okay? The only time you're going to see the xy part usually is if you have specific values that you want to evaluate. And we'll talk about the evaluation part momentarily. Most of the time, you're just going to see f sub x, and f sub y. And that's another way of saying partial derivative with respect to x, partial derivative with respect to y. So for instance here, for this first example, you're given an f of xy is 5x to the 4th minus 2x squared y cubed minus 4y squared. They want you to do f sub x of xy, which means they want you to find the partial derivative with respect to x. So as I go through this, The derivative of 5x to the fourth with respect to x is 20x cubed. For the next one, this is treated as a constant multiple, so that's why you still see it down here. And it's doing that funky thing that I hate. So this comes along for the ride. The derivative of 2x squared is 4x, so I end up with 4xy cubed. The minus sign still says minus. This, however, was a constant, because there's no x value there, so this is all treated as a constant. And its derivative would be 0. So if I'm doing a derivative with respect to x, I end up with 20x cubed minus 4xy cubed. That's why I have to be very careful knowing which variable I'm treating as a constant, which one I'm treating as the variable. So for your turn, same function. Now I want you to do f sub y of xy, which is the partial derivative with respect to y. Well, for this one here, this is a constant. So when I do fy, that's going to become a 0, minus, this is all constant, so I'm just going to keep that along for the ride. The derivative of y cubed with respect to y is going to be 3y squared. Notice I'm not putting a dy dx or a y prime following this because I'm doing the derivative with respect to y. I'm not treating y as a function of x. So that's one thing you get to keep in mind. But I don't have, I can't, here we're not treating y as a function of x and x as a function of y. These are independent variables. So, and now this one here, the derivative of 4y squared with respect to y is going to be 8y. So doing a little prettying up here, I'm going to have negative 6 x squared y squared minus 8y. Now, evaluating a partial derivative, much like when we dealt with doing regular derivatives, make sure that whenever you have to evaluate it for a specific value, that you also make sure that you differentiate first and then evaluate. I've had a couple of students on previous tests, they would plug in numbers first, evaluate, and then try to take a derivative, but you're taking a derivative of a constant at that point, and that's just going to be 0. So you have to figure out what the derivative is first and then evaluate it. So for instance, in this case here, you're asked to do the partial derivative with respect to y, evaluate it at 1, 3 for the function f of xy equaling e to the x squared plus y squared power. So first we take the partial derivative with respect to y. E to the x squared plus y squared power, the e to the power part just becomes e to that same power times the derivative of the exponent. Since x squared is being treated as a constant here because we're doing a partial derivative with respect to y, it's treated as a constant, it becomes 0. The derivative of y squared with respect to y is going to be 2y. So now I have my expression. Now I plug in the numbers. So I put the 1 and the 3 in their appropriate spots. I end up with e to the 10th times 6, or 6 times e to the 10th. So now it's your turn. I need to find the partial derivative with respect to x and evaluate it at 1, 0 if f of xy is xy minus 1 to the 5th power. So for this one here, now this is where it gets a little tricky because obviously, one way is to multiply this out 5 times, which is something we're trying to avoid. And I mentioned before that we don't treat y necessarily as a function of x, so I don't necessarily do the same thing I do with implicit differentiation. But now if I have a quantity being, raised to a power, if I have a quantity, being natural logged or e to a power, I still use the chain rule for that. So when I do the partial derivative with respect to x, I'm still going to do 5 times this x times y minus 1 to the 4th power, and then I'm going to do a derivative of what's inside there. Now, here's where it comes in. I'm not going to use the product rule when I differentiate x, y, because again, in this case here, y is just a constant. So when I do the derivative of x, y, I just end up with y. The derivative of 1 is 0, so I'd be subtracting 0, which I don't have to do. So, this is just 5y times xy minus 1 to the 4th power. So now when I do f of x 1 comma 0, I'm going to have 5 times 0 times 1 times 0 minus 1 to the 4th. Well, the fact that I have a 5 times 0 out here doesn't matter what the rest of it becomes. This is just going to end up being 0. So that's how you evaluate that. And, we could do partial derivatives with other variables. Again, when we do partial derivatives, like this one here, to give an example, with respect to x, the y to the 4th, z to the 5th is just a constant. We treat it as a constant. It's a constant multiple. So I would just do 3x squared times the rest of it, and that's all there is to it. Interpreting partial derivatives as rates of change. If I have more than one variable going on, and there's two things that are dependent upon, or something that's dependent upon two different things, then, I could have instantaneous rates of change with respect to one variable at a time. So, for instance, if I was looking at production in terms of L and K, this is the Cobbs-Douglas production function. I'm not going to do a lot of examples with this until we get to dealing with situations where they want us to, do more with it. But basically, we have L, which represents units of labor, and K represents the number of units of capital. So, it kind of gets similar to what we used to do for related rates. If I have labor, increasing at so many workers per day, that might affect the production. The production hopefully would go up, because I have more people working on it. So if I'm doing a derivative with respect to labor, then I could do it that way. I could also do the production with respect to capital. So I say if I put more money into the business, is that going to increase, decrease production? It really depends on the circumstance. So, you could do two partial derivatives and they mean different things. Sometimes you have to make sure you interpret them correctly. But they're their own rate of change, So, if I do a partial derivative of this with respect to L, I'll be doing, the rate of change of production with respect to, or it'd be production per labor increase or labor change, that sort of thing. And the other one would be, production per dollars capital. So find and interpret PL of 120, 200 and PK 120, 200 for the Cobb-Douglas function P of L, K. And there's the function they give you. So first off, in each one of these cases, I have to figure out what the partial derivative is. So PL equals 12L to the negative 0.04 power, K to the 0.4 power. Again, K to the 0.4 was treated as a constant here. We're doing the derivative with respect to L. Now when I put those values in, I get 14.7. So, interpreting what this means, the production increases by 14.7 units for each additional unit of labor. Whatever those units may be. They don't really define what they are. So production increases by 14.7 units for each new unit of labor that's added to the mix. Whereas when I do, they call this the marginal productivity of labor. When I do the partial derivative with respect to K, now the L to the 0.6 power is a constant. We get up with 8L to the 0.6, K to the negative 0.6. Again, we took 1 away from we multiplied this whole function by the original exponent, which was 0.4. We then subtracted 1 from the exponent of k. The L to the 0.6 was treated as a constant. So that's the derivative with respect to k. So that when I evaluate at 120, 200, I get 5.9. So that means the productivity for this instance is going to increase by 5.9 units for each increase in units of capital. So this is the marginal productivity of capital. And they go into, interpreting partials as marginals and things like that. So don't necessarily worry about this too much. Let's have a look at this. And this applies beyond the Cobbs-Douglas function and things like that. Here we have the resistance of blood flowing through an artery of radius r and length L, both in centimeters. So they want you to figure out, given that r is a function where r of little r comma L is 0.08 L r to the negative 4 power. They want us to find the partial derivative with respect to r at 0.54 and interpret it the meaning, and the partial derivative of this function at L at 0.54 and interpret its meaning. So, I want you to figure out part A first. In part A, what is the partial derivative with respect to r evaluated at 0.54, and give me a meaning for this number. Well, if I evaluate this, well, first I'm going to not focus on the 0.54. Not worry about that right now. Let's get my derivative function first. The L is going to be treated as a constant, so this 0.08 L is going to stay right there. When I do the derivative of r to the negative 4 power, I'm going to have negative 4 r to the negative 5 power, which is going to be a negative 0.32 L r to the negative 5. So now, when I evaluate that at 0.5, comma 4, I'm going to have negative 0.32 times L, which is 4, times 0.5 to the negative 5 power. When I multiply that all together, I get a negative 40.96. So as far as interpreting the meaning, this means that the resistance of blood flow decreases by 40.96 units, whatever that might be, I'm not sure, for each centimeter increase in radius. So if I increase, basically it means if I increase the radius of the artery by a centimeter, I'm going to get 40.96 less units of resistance, whatever it's measured in. Which means it's going to go down. I should have less resistance if I have a bigger area or a bigger, space for the blood to flow through. Stands to reason. Now, if I do the same derivative with respect to L now, Now, L is being treated as the variable, r to the negative 4 is a constant. So basically, the derivative with respect to L is going to be 0.08 r to the negative 4, which is all a constant. The L just goes away because it's derivative. That's it. So now, if I do RL at 0.54, I get 0.08 times. Now, again, I have R here and L here. I'm not going to use the value of L because I don't have any L's to put it into. I just have R, and that gives me 1.28, which means, as interpreted, the resistance of blood flow increases by 1.28 units for each centimeter increase. Why? In length of the artery. So basically, there's going to be more resistance because it has to go a further distance, you know, through the artery in that kind of situation. So some more information about slopes and stuff like that. Again, this graphical stuff they kind of put in there to kind of show the math behind it. You're not going to be asked to deal much with it, so I would say don't worry about it. Higher order partial derivatives, though, are something we're going to be using when we start looking for, you know, optimization. So when I look at this subscript notation, now you have to keep them. These two are easy to do because it's basically like me saying the second derivative with respect to x, the second derivative with respect to y. These are easy. Most people don't have trouble understanding this because it means I'm just going to do the derivative with respect to x and then take that answer and do the derivative with respect to x again. Same thing with fyy, or f sub yy, I should say. These ones here, it's different than we're used to doing. Usually, if we have things listed in order, we always work our way from like the inside to the outside. Sometimes that means going from right to left because we're used to doing like function notation. If we're doing like, you know, for instance, kind of going back to f of g of x, yeah, we would often deal with g of x first and either substitute or do what we have to do, evaluate it, whatever the case may be, and then take that result and then put it into f. We're kind of used to working that way. When I do the subscript notation, this means I'm going to do the derivative with respect to x first, and then, so that's first, and then y second. And this, of course, this is first, and that's second. So don't confuse the subscript notation with what we do for standard function notation. Sometimes students do that and they end up doing the wrong derivatives of this. So for 9, example 9, they want you to find all 4 second order partials for this. Now for me to get started, I have to first figure out what f sub x and f sub y are. Okay. Well, I mean, to do fxx and fxy, starting with this, you know, I could deal with it because I do a derivative of what's up here with respect to x. The x to the fourth becomes a 4x cubed. The 2x squared, y squared, the y squared is treated as a constant. So when I do the derivative of 2x squared, I get 4x. That y squared comes down as a constant multiple. The x cubed y, again, with respect to x, I end up with 3x squared y. The y a constant multiple. The y to the fourth is treated as a constant, so when I do the derivative of respect to x, that just goes away. Now that I have, f sub x, when I do f sub x sub x, I'm going to do just basically take the derivative of this again with respect to x. So I'm going to end up with 12x squared. The 4x is going to become 4. The y squared is a constant. The 3x squared is going to just become 6x. The y again is a constant. fxy, again starting with this, I take the derivative of that with respect to y now. So the 4x cubed is a constant, so it goes away. The 4x squared y, the 4xy squared, the y squared is treated as a variable, the 4x is a constant. So I'm going to have 4x times 2y, which is going to be 8xy. And when I do a derivative of 3x squared y with respect to y, the y is a variable, the 3x squared is a constant, so I'm just left with the constant when I do a derivative. F sub y would be the derivative of this original with respect to y, so I end up with 4x squared y. The x to the fourth goes away, it's a constant. 4x squared y is what 2x squared y squared becomes. X cubed is what the x cubed y would become, and 4y cubed would be what the y to the fourth becomes. Now when I do fyx and fyy, I'll do fyy first. Fx squared y, when I take its derivative with respect to y, the y just goes away, becomes a constant of 1, so I'm left with 4x squared. The x cubed is a constant, that just becomes a 0. 4y cubed, do the derivative of that with respect to y, I end up with 12y squared. For fyx, I take the derivative of that with respect to x. I end up with 8xy because I'm doing the 4 and the y are treated as the constants in the first term, and the derivative of x squared is 2x. X cubed, the derivative of that with respect to x is 3x squared. The 4y cubed with respect to x is a constant, so that just goes away. One thing they want you to notice here is that fxy and fyx end up being the same thing, but it's not true for all functions. So they pointed it out here, and if anything, some cases and some derivatives that can happen, but don't expect it to be something that happens all the time. Okay, a lot of the functions you may look at, it might be the case, but again, don't assume it to happen all the time. So your turn in the last problem that you're going to be asked to do in this video. I want you to figure out what these 4 things are for fxy of 4x squared minus 3x cubed y squared plus 5y to the 5th. I want you to find f sub xx, f sub xy, f sub yx, and f sub yy. Okay, so for me to go through these, and before I get heavily involved with the rest of it, I'm going to first figure out what fx is, and fy. So when I do the derivative with respect to x, I'm going to end up with 8x minus 9x squared y, and the derivative of 5y to the 5th with respect to x, that's going to be treated as a constant, so it's 0. When I do fy, or f sub y, the 4x squared is a constant, so that's going to go away completely. I'm going to have negative 6x cubed y, and I'm going to have plus 25y to the fourth. So with these in place, I can now much more easily do fxx, fxy. Focusing on this one first, because that's what's going to, because each one of these, I'm assuming I did this part first for A and B. When I do the derivative of this with respect to x again, I'm going to end up with 8 minus 18xy. When I do f sub xy, I do the derivative of fx with respect to y. I end up with a constant as 8x, so that goes away. For this one here, I'm going to be left with, the derivative with respect to y. I end up with a negative 9x squared y. Oh, sorry, take that back. That's 9y squared there. That's, copying error. Kind of going back, because I just want to point out what I had done. This should still have a square here too, because I forgot to write the square down when I did the derivative of the 3x cubed y squared. The y squared should still stay y squared at that point. So now when I do the derivative with respect to y, I still end up with a 0 in the first position. I end up with negative 18x squared y. For these two down here, I'll use a different color. I'm now going to do this part here. I started with that part here, so I do the derivative of that with respect to x. I end up with negative 18x squared. The y is constant, so it comes along for the ride. Just like I mentioned before, sometimes, like this function, like the other one, it does have the same thing for this. Don't always assume that to happen. As far as f sub y goes, I do derivative with respect to y for that. I'm going to end up with negative 6x cubed plus 100 y cubed. And those are the partial derivatives. If you have any further questions, please make sure to contact me or bring it up in class. I'll see you around. Bye, everybody.